There was a recent report done by the Nuclear Energy Agency of the OECD on thorium systems. Can you make them work? Yes, you can make them work. Is there an advantage to doing it? I haven't seen it.
A new paper has just come out on thorium-powered nuclear reactors. Not quite so bullish on the case for thorium.
It's from Britain's National Nuclear Laboratory. So they say that there's about 4 times more thorium on Earth than there is uranium. But at the moment, uranium is cheap enough that that simply doesn't matter.
It's, I think, one of these sort of technological cults.
Melting the fuel rods down in concentrated nitric acid from the thorium reactor, extracting 233, and then making more fuel rods with that and putting it in another reactor. It's economically totally out of the question. Go to my webpage section on thorium reactors written by physicists.
You just heard 3 different reports cited. One to a Congressional Committee on Energy, one to readers of The Economist, and one to the audience of Russia Today. All 3 reports overwhelmingly focus on the challenge of consuming thorium in solid fuel reactors, such as Shippingport Atomic Power Station.
This reactor is going to cost something over $55 million, I believe. It will produce about 100,000 kilowatts of power.
The real object of this reactor is to learn about pressurized water reactors for atomic power. It will not be cheap to operate. It will be no cheaper to operate than Wright's Kitty Hawk would have been to carry passengers around. At the present time, reactor design is an art. It's not a science. We are trying to make a science out of it.
Rickover built one of these reactors and put it over here in Shippingport. A funny-looking submarine shell-shaped containment building.
Yeah, that's funny.
It is the first full-scale nuclear power plant for generation of electricity in the United States.
Over its 25-year life, Shippingport was powered by various combinations of nuclear fuel, including one fuel load of thorium.
He wanted to prove he could make a light water breeder.
He kind of snuck Radkowski in there to put the thorium in. The people in charge now of the AEC were not interested in the breeding.
The only problem is the core turned into a gigantic, humongous Swiss watch that had to be that accurate with 1 million little springs holding it all together. He was trying to shoehorn different nuclear physics into an existing system. It made it very complicated and very difficult to work. He did that under the Naval Reactor program. We used to have a separate Naval Reactors division here in this lab.
They developed and built the reactor for the world's first atomic submarine, the Nautilus. The story of the Nautilus is legend. Because of its success, it was used as a starting point in the development of an advanced design reactor for Shippingport. Its name, PWR, Pressurized Water Reactor.
The reason we have that as the base for our power reactor technology today is because the Navy was prepared to pay the first mover costs to make one work. And once you've done that, it's extraordinarily difficult to compete with it because those first mover costs are very, very high and have no financial return associated with them.
I became really quite friendly with Rickover. He spent better than a year, and that's where he learned about nuclear power.
See, was that about 1947?
It was 1947, yes. And it was I who urged on Rickover that the way to make a nuclear-powered submarine was with a pressurized water reactor.
You know, the Navy had reactors, and so the Air Force had to have reactors.
The Navy has built their nuclear submarines, and the Army has taken the same technology as the Navy, the water-cooled reactor, and they're doing their thing, but the Air Force wants to build a nuclear-powered bomber.
Dirty little secret was that most of the people involved in it knew from the get-go that it really wasn't practical. In contrast to a submarine where you've got limited space, but you can shield it for the people on the submarine, it's much harder on an airplane because of the weight.
Most of us did not really think that the aircraft reactor really could work. But we did feel that there was a very interesting technology there that someday could be applied.
And I would maintain that Weinberg was absolutely right in his assessment of the situation back then. He knew that to make the nuclear airplane work, they couldn't use water-cooled reactors. They couldn't use high pressure reactors. They couldn't use complicated solid fuel reactors. They had to have something that was so slick, that was so safe, that was so simple, that operated at low pressure, high temperatures, had all the features you wanted in it. They didn't even know what it was. I think someday this will be looked at as one of the great pivot points of history, that if this program, this nuclear airplane program, had not been established, the molten salt reactor would have never been invented, because it is simply too radical, too different, too completely out of the ball field of everything else for it to be arrived at through an evolutionary development. It had to be forced into existence by requirements that were so difficult to achieve, and the nuclear airplane was that.
Well, we were young chemical engineers at the time, and God smiles on young chemical engineers. They do things that in later years would be regarded as crazy.
The Navy program that led to the light water reactors we have now was well optimized to the needs of the Navy. It actually wasn't very well optimized to the needs of power production.
The reactor category advocated by Alvin Weinberg for civilian power production, the molten salt reactor, is covered in only 2 of the 3 reports dismissing thorium.
But they were very convincing.
Yeah, they're idiots. These people are mad. Now let me tell you about thorium. To produce electricity, you have to reprocess, like melt the fuel, then make the fuel rods with uranium-233 and put them in a reactor. It's economically totally out of this question. So these men are mad. There's some sort of psychotic element in the nuclear industry to do with testosterone and hormone receptors in the brain and behaviour, and sex comes into it.
E equals mc squared is a substitute probably for male, will I say it? Erection and ejaculation. And they like it, and it's this sort of energy that really grabs them.
So let's dismiss that 3rd report by the anti-nuclear organization IEER and focus on the NNL and OECD reports. They do include sections on molten salt. The United Kingdom's NNL report correctly identifies the advantages offered by molten salt reactors in its molten salt reactor section. That is, page 23. However, the full implications of molten salt reactors are not examined throughout the different sections. For example, proliferation risk and reprocessing are covered as if spent fuel containing uranium-233 will be shuttled between the reactor, a reprocessing facility, and a spent fuel repository. That is not the case. Uranium-233 is both created and fissioned into energy inside the reactor itself. Unlike solid fuel alternatives, what emerges from the molten salt breeder does not represent a proliferation risk, nor a reprocessing challenge. A single part of the NNL report illustrates how this should have gone. Page 18. Recycling U-233 presents some difficult challenges in fuel fabrication because of the daughter products from U-232. Problems, challenges, technological barriers, technical risk. And then, at the bottom, MSR is unique in that it avoids these problems entirely with no fuel fabrication required. The NNL report could easily have a caveat carved out in every section regarding molten salt reactors. MSR impacts every aspect of the thorium fuel cycle, including proliferation. From a liquid fuel perspective, there's no meat in this report. The OECD report is another report focused on solid fuel. Like the NNL report, every section goes into detail about the challenges of thorium with solid fuel reactors. But it does offer a fairly meaty section on molten salt reactors. 11 pages. Does the OECD report evaluate Alvin Weinberg's concept of the molten salt breeder and identify technical challenges which may impede development? Of those 11 pages in a 133-page report, 1 sentence does so. This 1 gigawatt design was a thermal reactor with graphite-moderated core that required heavy chemical fuel salt treatment with a removal time of approximately 30 days for soluble fission products. A drawback that could potentially be eliminated by using a fast spectrum instead. The remaining 10 pages of molten salt are then entirely dedicated to a different molten salt reactor concept, a fast spectrum molten salt reactor. If you don't know the meaning of moderator, fast spectrum, or fission products, then please bear with me. These terms will be explained. In a fast spectrum reactor, uranium and thorium perform the same. In a solid fuel reactor, uranium is a superior choice. It is only in Alvin Weinberg's thermal spectrum molten salt breeder reactor that thorium's advantages become clear.
And this is what I think is really worthy of consideration. Right now, we have to make an economic case for why should we consider thorium as a fuel source. We can go and we can mine uranium and we can enrich it and we can essentially burn out the small amount of uranium-235 in that. And you can put an economic quantification on the value of a gram of fissile material in the form of LEU. It's on the order of $10 to $15 out of the ground. That's what a gram of U-235 in that fuel represents. So if you want to make an economic case for why you're going to use the thorium fuel cycle, you better figure out how to turn a gram of thorium into fissile and fission it for less money than that. Otherwise, nobody's really going to care from an economic basis. And so this is why we want to pursue radical simplification in the reprocessing. We want to make it as simple as we possibly can, but no simpler.
The OECD report evaluates thorium based only on solid fuel reactors and fast spectrum molten salt reactors. It does not evaluate thorium based on Alvin Weinberg's molten salt breeder reactor.
When the idea of the breeder was first suggested in 1943, the rapid and efficient recycle of the partially spent core was regarded as the main problem. Nothing has happened in the ensuing quarter century that has fundamentally changed this. And I'll go further. Nothing has happened in the ensuing 40 years that has fundamentally changed this. Weinberg nailed the basic idea.
The media overlooked this gaping hole in the report, no mention of Alvin Weinberg, the molten salt reactor experiment, or of liquid chemistry. No mention of a buried sentence in the 100-page report. Let's reword it for clarity. This 1 gigawatt design was a thermal reactor with graphite-moderated core that avoided the drawbacks of fast spectrum by removing soluble fission products through the use of chemical fuel salt treatment.
The successful breeder will be the one that can deal with the spent fuel most rationally, either by achieving extremely long burnup or by greatly simplifying the entire recycle step. We at Oak Ridge have always been intrigued by this latter possibility. It explains our long commitment to liquid-fueled reactors, first the aqueous homogeneous and now the molten salt.
The second reactor actually operated very well. That was the molten salt reactor experiment.
There it is. This is the place.
These things right over here are the spent probes. See, those things would extend to like 60 foot in length. They went down the tank, did the melting, did this bubbling and stirring and everything.
One of the things that I've learned from talking to some of the old timers, people didn't disbelieve that we could build the machine. They didn't believe that we could maintain it.
Operation of the MSRE was not too difficult, and the people that I had working for me, they all had pound dogs under the porch. Old cars out in the yard that didn't run very well. If anything came up side of the molten salt reactor, they said, "We fix that," and they did.
He felt like, despite the challenge of operating high radiation fields, that they were able to operate and maintain that machine over the course of its lifetime.
I started out at the lab in 1957 and got onto the molten salt reactor experiment. The dynamics were not common to reactors because it was molten salt instead of water-cooled solid fuel. If it heats up, it gets less dense, and that means it's less critical.
Or less reactive.
Yeah, less reactive.
Yeah. I was running some tests late at night. The device that I was using got stuck in the wrong place and pulled the rod out, and the power went up and up beyond the design power, and then controlled itself and went back down. Wow. Everybody was happy.
After they completed the molten salt reactor experiment, they went to the Atomic Energy Commission. They said, hey, gee, can we have some more money? We'd like to go now and build the real thing. We'd like to build the core, and we'd like to build the blanket, and we'd like to hook a power conversion system on and make electricity. And so they felt like they'd shot the moon. Well, the Atomic Energy Commission, unfortunately, did not share their zeal to continue with the technology. In addition to being a thorium guru, Weinberg was also the original inventor of the pressurized water reactor. He had invented it and gotten his patent for it in 1947. It was a little bit of a tricky thing to have the inventor of the light water reactor advocating for something very, very, very different. He didn't like the fact that it had to run at really high pressure. He just he saw that as a risk.
As long as the reactor was as small as the submarine intermediate reactor, which was only 60 megawatts, then containment shell was absolute. It was safe. But when you went to 1,000 megawatt reactors, you could not guarantee this.
He figured there would be an accident someday where you were not able to maintain the pressure or keep cooling it.
In some very remote situation, conceive of the containment being breached.
Does any of this sound familiar? He was making enough of a stink about this that a congressional leader named Chet Holofield told Alvin Weinberg, he said, if you're so concerned about the safety of nuclear energy, it might be time for you to leave the nuclear business. And Weinberg was really kind of horrified that they would have this response to him because he wasn't questioning the value or the importance of nuclear energy. If anything, he was far more convinced about that than anyone else. What he was questioning had the right path been taken in the development of nuclear reactors.
Do you feel like the program had a sound technical basis, or do you feel like technical problems were the basis for cancellation?
Some of the technical reasoning that I heard for the cancellation was that there was a corrosion problem.
Tritium was raised as another issue. We made no effort on MSRE to do anything with tritium.
Did the people on the program feel like tritium was an insurmountable problem?
We recognized that tritium would have to be captured, but most people thought that that's something that we should be able to do.
Did the people on the program, particularly the chemists or the material scientists, feel that corrosion was an insurmountable problem on the program?
No. Some of the subsequent experimental work seemed to bode very favorably for an ability to solve that issue. As well as the tritium issue, by the way, because we did do some tritium experiments.
Were either of you present when the molten salt reactor program was canceled in the early 70s?
Yeah, we were still working there.
Well, I was still working on the system. We were still finalizing reports on the performance of the MSRE.
I didn't see it coming.
Mr. President, since you missed our meeting on breeder reactor, we sent the message today, Craig. I told Ziegler to tell the press that it's a bipartisan effort. This has got to be something we play very close to the vest. But I am being ruthless on one thing. Any activities that we possibly can should be placed in Southern California. So on the committee, every time you have a chance, needle them, say, where's this going to be? Let's push the California thing. You do that?
Nixon was from California. Hosmer was from Southern California. Chet Holofield, who ran the Joint Committee on Atomic Energy, was also from California. It doesn't lead me to believe that the president was seriously considering alternatives to the fast breeder reactor and other paths that could be taken. It was a focus on what can we do right now to get jobs.
Now, don't ask me what a breeder reactor is. All of this business about breeder reactors and nuclear energy and the stuff is over my head. That was one of my poorest subjects, science, and I got through it, but I had to work too hard. I gave it up when I was about a sophomore. But what I do know is this, that here we have the potentiality of a whole new breakthrough in the development of power for peace.
The fellow on the phone call that we heard earlier said that if cost targets were missed, I, for one, don't intend to scream and holler about it. In that same month, the Atomic Energy Commission issued WASH 1222. It almost completely ignored the safety and economic improvements possible through the use of the molten salt breeder reactor technology.
Milton Shaw, who was the head of reactor development in Washington, called up and says, stop that MSRE reactor experiment, fire everybody, just tell them to clear out their desk and go home. and send me the money for fast breeders.
Any other place, like if as an organization, okay, well, we're abandoning this route and going another, well, it just gets lost. It's amazing how much they documented.
Enormous amounts of detail about the work that had been accomplished and how they had developed the technology.
Almost all of the nuclear power we use on Earth today uses water as a basic coolant. It's a covalently bonded substance. The oxygen has a covalent bond with two hydrogens. Well, neither one of those bonds is strong enough to survive getting smacked around by a gamma or a neutron. And sure enough, they knock the hydrogens clean off. Now, in a water-cooled reactor, you have a system called a recombiner that will take the hydrogen gas and the oxygen gas that is always being created from the nuclear reaction and put them back together. It's a great system as long as it's operating and the system is pumping. Well, at Fukushima Daiichi, the problem was the pumping power stopped.
At high temperature, H2O can also react with the cladding to release hydrogen, or damage the cladding, releasing radioactive isotopes. These two accidents illustrate the need for a coolant, which is more chemically stable than H2O. 3 Mile Island, Chernobyl, and Fukushima were all radically different incidents. But what all three had in common was how poorly water performed as a coolant when things started to go wrong.
Steam takes up about 1,000 times more volume than liquid water. If you have liquid water at 300 degrees Celsius and suddenly you depressurize it, it doesn't stay liquid for very long. It flashes into steam.
That's a scuba tank, hot scuba tank, full of nuclear material.
At 3 Mile Island, water couldn't be pumped into the core because some of the coolant water had vaporized into steam. The increased pressure forced coolant water back out, contributing to a partial meltdown. At Chernobyl, the insertion of poorly designed control rods caused core temperature to skyrocket. The boiling point of the pressurized water coolant was passed, and it flashed to steam. It was a steam explosion that tore the 2,000-ton lid off the reactor casing and shot it up through the roof of the building. At Fukushima, loss of pump power allowed coolant water to get hotter and hotter until it boiled away. These three accidents illustrate the need for a coolant with a higher boiling point than water.
When you put water under extreme pressure, like anything else, it wants to get out of that extreme pressure. Almost all of the aspects of our nuclear reactors today that we find the most challenging can be traced back to the need to have pressurized water. Water-cooled reactors have another additional challenge. They need to be near large bodies of water where the steam they generate can be cooled and condensed. Otherwise, they can't generate electrical power. See, I had the good fortune to learn about a different form of nuclear power that doesn't have all these problems for a very simple reason. It's not based on water cooling, and it doesn't use solid fuel. Surprisingly, it's based on salt.
Science allows you to look at everyday objects for what they really are, chemically and physically. And it really makes you look twice at the world around you. Your table salt is frozen. That's a really strange thing to think about. Your table salt on your kitchen table it's frozen.
But once they melt, they have 1,000 degrees C of liquid range. And they have excellent heat transfer properties. They can carry a lot of heat per unit volume, just like water. Water actually is really good from a heat transfer perspective. It's good at carrying heat per unit volume. Salts are just as good at carrying heat per unit volume, but salts don't have to be pressurized. And that, if you remember nothing else of what I say tonight, remember that one fact. A nuclear reactor is a rough place for normal matter. The nice thing about a salt is it's formed from a positive ion and a negative ion. Like sodium's positively charged and chlorine's negatively charged. And they go, we're not really going to bond. We're just going to kind of associate one with another, you know. And that's what's called an ionic bond. Yeah, you're kind of friends, you know. You're
Facebook friends.
Facebook friends. All right, well, it turns out this is a really good thing for a reactor because a reactor is going to take those guys and just smack them all over the place with gammas and neutrons and everything. And the good news is they don't really care who they particularly are next to. As long as there's an equal number of positive ions and negative ions, the big picture is happy. A salt is composed of the stuff that's in this column, the halogens, and the stuff that's in these columns, the alkalis and the alkaline earths. Fluorine is so reactive with everything, but once it's made a salt, a fluoride, then it's incredibly chemically stable and non-reactive.
Sodium chloride, table salt, or potassium iodide, they have really high melting points. And we like the lower melting points of fluoride salts.
Human mechanical energy is so amazing. Why can't we use that to create energy? You will never run out of electricity. You never generate any pollution. So half the world is not going to generate pollution. We call it free electric.
Solar freaking roadways. Replaces all roadways, parking lots, sidewalks, driveways, tarmacs, bike paths, and outdoor recreation surfaces with smart microprocessing interlocking hexagonal solar units.
Maintaining a nation of solar highways. Manufacturing bicycle battery generators for every home.
An extremely ambitious idea to replace our nation's roads with solar panels.
The Department of Transportation has kicked in $850,000. People are actually taking this seriously.
Despite the media attention they've received, I think these ideas are flat out crazy. But they're par for the course in today's energy landscape.
The Keystone XL pipeline extension.
For a while, the entire national energy discussion revolved around a single pipeline. Sometimes, it seems, the more difficult an energy source is to harness, the more attention it receives.
If you'll give me a chance to serve, I'll bring the EPA and the Agriculture Department and all the people together, and we'll use ethanol as a part of our nation's energy security future.
Even Al Gore, who was a key proponent of corn ethanol, acknowledges the subsidy was a mistake. The energy conversion ratios are, at best, very small. How does corn's 1.3 times compare against other energy sources? Solar cells return 7 times. Natural gas is 10 times. Wind is 18 times. Today's water-cooled nuclear is 80 times. Coal is 80 times. Hydropower is 100 times. A thorium-powered molten salt reactor can return 2,000 times the energy invested in it.
Let's take a peek at a future powered by nuclear. This is a little weird.
We can radically cut climate change emissions and leave a safe, clean world to the future. We don't need to invent anything new. We just need to stop wasting time with distractions like nuclear power. Come on, let's build the future we all want to see.
To understand why nuclear power has so much potential requires some effort. It requires you to exercise a little bit of study. Which part of this is doable and could be safe and could be acceptable in our society, and which part of this is not. And there's a collage of images that the anti-nuclear movement will throw at you, usually of nuclear weapons. I hate nuclear weapons. I never want to see nuclear weapons used. I have no interest in that. But I do want to see nuclear power used to make my life and my children's lives and your children's lives safer and better.
Think of the sun's heat on your upturned face on a cloudless summer's day. From 150 million kilometers away, we recognize its power.
When's the last time you watched Cosmos with Carl Sagan?
Recently, actually.
Really?
Yeah, I showed it to my kids a couple of years ago. Empire Strikes Back and Cosmos were probably two of my formative influences at the age of 6.
The sun is the nearest star, a glowing sphere of gas. The surface we see in ordinary visible light is at 6,000 degrees centigrade. But in its hidden interior,
superhot gas pushes the sun to expand outward. At the same time, the sun's own gravity pulls it inward to contract. A stable equilibrium between gravity and nuclear fire.
atoms are made in the insides of stars.
The atoms are moving so fast that when they collide, they fuse. Helium is the ash of the sun's nuclear furnace. Sun is a medium-sized star. Its core is only a lukewarm 10 million degrees. Hot enough to fuse hydrogen, but too cold to fuse helium. There are many stars in the galaxy, more massive yet, that live fast and die young in cataclysmic supernova explosions. Those explosions are far hotter than the core of the sun. Hot enough to transform elements like iron into all the heavier ones and spew them into space. Long before the Earth, our home was built. Stars brought forth its substance.
Our planet, our society, and we ourselves are built of star stuff.
Now, two of the things that were created in supernova are thorium and uranium. These were different because they were radioactive, and they kept some of that energy from the supernova explosion stored in their very nuclear structure. And some of this thorium and uranium was incorporated into our planet, sinking to the center of the world and heating our planet.
Liquid iron circulating around the solid part of the core as Earth rotates acts like a wire carrying an electric current. Electric currents produce magnetic fields, and that's a good thing. Our magnetic field protects us from the onslaught of cosmic rays.
Bigger deal, the magnetic field is deflecting the solar wind. If you don't have a magnetic field deflecting the solar wind, over billions of years your planet ends up like Mars, because the solar wind will strip off a planet's atmosphere without the protecting nature of the magnetic field. So if we didn't have the energy from thorium inside the Earth, we would be on a dead planet.
The decay of radioactive elements in the core keeps it moving.
Let's talk about radioactivity, because I had an erroneous notion of what radioactivity was. I thought that if you had something that had like a half-life of a day, and you had something that had a half-life of 1,000,000 years, it meant that the dude that was radioactive for a day is like for a day, and then I'm done. And the dude who's half-life for 1,000,000 years is like for 1,000,000 years, and then done. Okay, so you go, well, which one of these is more dangerous? Well, definitely the one that's got a half-life of 1,000,000 years, because that's got to be like radioactive forever, and the dude's radioactive for a day, that's not a big deal, right? Completely wrong. Okay, utterly backwards. The dude who's radioactive for a day is really, really radioactive. The dude who's radioactive for 1,000,000 years is hardly radioactive at all. Which one of those two is more dangerous? The one that's radioactive for a day, by a long shot. Okay, so your radioactivity is directly and inversely proportional to your half-life. So somebody goes to you, there's something that's got a half-life of 1,000,000 years. Scary, huh? And you give it to me, I'll put it in my hand. It's not gonna hurt me. It's not gonna hurt me. There's something that's a half-life of a day. You wanna hold, no, keep it away from me, man. That stuff is hot, but it's going away fast too, right? It's got a longer half-life, it's less dangerous.
And I want to tear my hair out because what I haven't mentioned is radioactive waste.
All our radioactive waste?
The main problem is radioactive waste. Close down all those reactors now with solar and wind and geothermal.
Geothermal.
What's green energy? And they go, geothermal's green energy. Okay. Do you know where geothermal comes from? No. It comes from decay of thorium inside the Earth. Oh. Is geothermal renewable? Yes. Okay, then thorium's renewable. No, it's not. You're using it up. Well, you're using up thorium as it decays inside the Earth. Any argument for geothermal, if it is rigorously pursued, is an argument for the renewability of thorium as an energy resource.
The majority of American geothermal is harvested in the state of California, which has most of its geothermal energy harvested in the Imperial Valley. A typical Imperial Valley geothermal plant produces 40 tons of radioactive waste every day.
They're saddled with all our radioactive waste. Who do we think we are, Bob?
Geothermal is creating 200 times the volume of radioactive waste that nuclear reactors do per watt of power.
I don't want to wear a dosimeter. Don't calculate rems and sievers. I don't want to see no cleanup crews. Or get zapped before I hear the news. We can get the heat from Earth and Sun. And hook the wind to make the engines run. If common sense could only start a chain reaction of the human heart. What a wonderful world this would be.
Coal and gas plants are able to release radioactive materials to the environment in much greater amounts than a nuclear plant would ever possibly be allowed to, because they are considered what's called NORM, naturally occurring radioactive materials. For instance, when you go frack a shale and you pull gas out, a lot of radon comes out with that too. You burn the gas, that radon's being released. Nobody counts that radon against the gas. If they did, the Regulatory Commission would shut the gas plant down. Same with coal. And they've spent a lot of money to make sure that regulatory agencies do not regulate NORM for a coal or a gas plant the way they regulate radioactive emissions from a nuclear plant. If they did, we would be shutting down all our coal and gas plants based on radioactivity alone.
A fear of radiation probably is the basis of most fear of nuclear power in general. What is radiation? It's simply the idea that there are certain nuclei that radiate things from them. In the process of changing to something else, they radiate something.
Modern physics and chemistry have reduced the complexity of the sensible world to an astonishing simplicity. 3 units put together in different patterns make essentially everything. A proton has a positive electrical charge. A neutron is electrically neutral. And an electron, an equal negative electrical charge. Since every atom is electrically neutral, the number of protons in the nucleus must equal the number of electrons far away in the electron cloud. The protons and neutrons together make up the nucleus of the atom. If you're an atom and you have just 1 proton, you're hydrogen. 2 protons, helium, 3 lithium, all the way to 92 protons, in which case your name is uranium.
For any given element, the number of protons must remain the same, but the number of neutrons may vary. The atomic weight of an atom is the number of protons plus the number of neutrons. Natural uranium may contain 142, 143, or 146 neutrons. That means uranium has 3 natural isotopes, U-234, U-235, and U-238. Some elements, such as tin, have a great number of natural isotopes. Others, such as aluminum, have only 1. Most isotopes are stable. They would never spontaneously change their atomic structure. But some isotopes are constantly changing. They're busy being radioactive. Given enough time, this radium-88 isotope will shed energy and change. This is how isotopes in the Earth itself emit radiation. The Geiger counter detects their presence. A cloud chamber makes these rays visible to the naked eye. Each new vapor trail shows that another atom has thrown off a fragment from its nucleus. Each atom does this only once before becoming a different isotope. This activity appears to go on endlessly. That's because there's billions of atoms in that tiny sample.
You can't turn decay on and off. If we can turn radioactive decay on and off, we could do all kinds of things, but we've never figured out how to do it. I don't think we ever will, because we simply can't influence the state of the nucleus like that.
Hit it with a hammer. Boil it in oil. Vaporize it. The nucleus of an atom is a kind of sanctuary, immune to the shocks and upheavals of its environment. The atoms of each unstable element decay at a constant rate.
These mousetraps represent atoms that are radioactive. Every once in a while, a mousetrap spring breaks down and snaps shut. A tiny bit of mass is converted into energy as an atom changes spontaneously into a lighter isotope.
Thorium has only 1 isotope, thorium-232. It has a 14 billion year half-life. Okay, so when the universe is twice as old as it is now, thorium will have only decayed 1 half-life. So based on what I just told you about radioactivity, what does that tell you about how radioactive thorium is? Hardly at all. Okay, uranium, 2 isotopes, uranium-235, uranium-238. Both, of course, are radioactive. U-238 has a 5 billion year half-life. That's pretty old. That's about how old the Earth is. That's how old the Earth is. That's how old the universe is. Uranium-235, on the other hand, much shorter half-life, 700 million years. This is a handful of these uranium oxide fuel pellets. And you see the picture, the guy's got gloves on, and so you think, oh, he's got gloves on to protect him from the uranium oxide. But now that I've taught you about the true nature of radioactivity, you might go, Kirk, I'm not so sure that stuff's so dangerous after all. And you would be correct. He's not protecting himself from the uranium, he's protecting the uranium from himself. That stuff has to stay super pure and super clean, and you don't want to get any of your oils or grease or sweat on nuclear fuel that's going to go inside a fuel rod. So that's what the gloves are for.
Knowing that some atoms could spontaneously change, in 1939, scientists tried firing a neutron into the nucleus of a uranium atom, the heaviest and least stable atom found in nature. Instead of a minor change from one isotope into another, the uranium atom split into two parts. When an atom is so unstable that it can be split into two by hitting it with a neutron, we call that fissile. When the fissile uranium atom split apart, those two parts combined were lighter than the original uranium atom. The missing mass was converted into energy. Also released were two neutrons. One free neutron has become two free neutrons.
Now we have two neutrons. This implied a nuclear chain reaction in uranium.
Somebody wondered one time, okay, billions of years ago, that means there was a lot more uranium-235, and natural nuclear reactors might have been possible.
When you generate electricity from nuclear power, you make 200 new elements that never existed before we fissioned uranium.
We found in Africa, at a place called Oklo in the Gabon, 2 billion years ago, there were scores of natural nuclear reactors there. There were nothing more than uranium ore in the rock, and the water would come in and it would lead to a nuclear reaction. And these reactors ran for hundreds of millions of years. So we did not invent nuclear fission, all right? It was done long, long, long before we were here, and very successfully. Back when the Earth was formed, there was a lot more uranium-235 than there is now. Uranium-235 is like silver and platinum. Can you imagine burning platinum for energy? And that's what we're doing with our nuclear energy sources today. We're burning this extremely rare stuff, and we're not burning the uranium-238 and the thorium.
Your uranium in Saskatchewan is so rich you don't even have to enrich it. It's extremely powerful.
Caldecott is wrong. There is no natural source of isotopically enriched uranium. Natural uranium's isotopic ratios are identical everywhere on Earth.
The amount of uranium in the world is finite. If all electricity today was generated with nuclear power, there would only be 9 years' supply of uranium left in the whole world.
In reality, there is no more a constrained uranium supply than there is a constrained seawater supply. Uranium is water-soluble, and it passes from the Earth's mantle to the crust to the ocean. Every year, the ocean contains more uranium than the previous year.
My straw reaches across the room.
We're pretty inventive when it comes to harvesting natural resources.
I drink your milkshake. I drink it up!
We are never going to run out of uranium. It is quite literally a renewable resource, for all the difference that distinction makes.
About 35 years worth of oil left in the whole world. We're going to run out of oil.
As a natural resource, the appeal of thorium over uranium is that thorium has zero environmental cost to acquire. We can power our civilization on thorium without opening a single thorium mine. It is already a plentiful byproduct of existing mining operations.
We need the thorium, and he needs somebody to get rid of the thorium.
It's found in tailings piles. It's found in ash piles.
Only one of the materials in nature is naturally fissile, and that's uranium-235, which is a very small amount of natural uranium, about 0.7%. This was the form of uranium that could be utilized directly in a nuclear reactor. Most of the uranium was uranium-238. This had to be transformed into another nuclear fuel called plutonium before it could be used. And then there was thorium. And in a similar manner to uranium-238, it also had to be transformed into another nuclear fuel, uranium-233, before it could be used in a reactor.
How much energy did the neutron have that you smacked the nuclear fuel with? Okay, how much energy did it have? And then how many neutrons did you kick out when you smacked it through fission?
2 is a very significant number in breeder reactors. You need 2 neutrons. You've got to have 1 to keep your process going, and you have to have another 1 to convert fertile material into fissile material.
Okay, look at plutonium. It's that dip below 2 right there. That's what makes it so you cannot burn up uranium-238 in a thermal spectrum reactor, like a water-cooled reactor. You just can't do it. The physics are against you. And the reality is you do lose some neutrons. You can't build a perfect reactor that doesn't lose any neutrons. So they looked at this and they said, man, we just can't burn uranium-238 in a thermal reactor. It just can't be done. Well, you know, these guys are undeterred. They said, well, here's what we'll do. We'll just build a fast reactor, because look how good it gets in the fast region. Wow, it gets above 2. If it gets to 3, wow, this is really good.
Well, there's a powerful disincentive to doing it this way, and it has to do with what are called cross-sections. These are a way of describing how likely it is that a nuclear reaction will proceed.
Look how much bigger the cross-sections are in thermal than they are in fast. How many of these little dots are we going to need to add up to this size? We're going to need a lot. So this is why it was a big deal to be able to have performance in this region of the curve. Those little bitty dots, they're up here in this part of the curve. Okay, this is the fast region. This is the thermal region.
Thorium is more abundant than uranium.
All we're consuming now is that very, very, very small sliver of natural uranium.
But this is not the big deal. No, it's not a big deal that natural thorium is hundreds of times more abundant than the very small sliver of fissile uranium. The big deal about thorium is that we can consume it in a thermal spectrum. That's the big deal of thorium, is that it can be consumed in a thermal spectrum reactor. When you're talking about a thermal spectrum reactor of any kind, you have to have fuel and you have to have moderator. And they're both essential to the operation of the reactor. The moderator is slowing down the neutrons. And when the neutrons have been slowed down, we call them thermal neutrons, or a thermal spectrum. In a water-cooled reactor, we use water, specifically the hydrogen in the water, to slow down the neutrons through collisions.
The graphite in the molten salt reactor, is that a moderator?
Yes, that's the moderator in the reactor.
Same idea, except we use graphite as the moderator instead of water.
Neutrons go in the graphite, hit the carbon atoms, they lose energy, they slow down.
Now why slow it down? That's the difference when you're going from that little bitty dot to the big dot. That's why you want to slow it down. You want the big dot, not the little bitty dot.
A thermal spectrum molten salt reactor has to have the graphite moderator of the core in order to sustain criticality. If the vessel ruptures, recriticality is fundamentally impossible. The drain tank does not have any graphite in it. If something happens where that fuel drains away from that graphite, criticality is no longer possible. The reactor's subcritical fission stops, and there's no way to restart it without reloading the fuel back into the core.
This is such a remarkable feature, and it really is unique to having this liquid fuel form and to having something that can operate at standard pressure. You can't do this in solid fuel. If you do this in solid fuel, it's called a meltdown.
If we had more of today's reactors in operation, 1 cup of uranium oxide would cover a typical American's yearly energy demand. Per capita, that's the equivalent of burning 54 barrels of oil every year for every single American, or 12 tons of coal, or 5,300 cubic feet of natural gas to generate the same amount of energy. 4 grams of thorium can power a middle-class American lifestyle for a full year. That's just 4 grams. But this can only happen if the reactor is efficiently fueled with chemically homogeneous liquid fuel, if the reactor runs at high temperature, and the power generator is optimized to take advantage of the reactor's high temperature operation.
The performance of the carbon dioxide gas turbine is such it leads to very, very compact turbo machinery. The turbo machinery for this entire reactor would easily fit on this stage, probably on half this stage. And if anybody's been to a big reactor before and seen big steam cycle turbo machinery, you can appreciate what a reduction in scale that is.
High efficiency power conversion enabled by the high operating temperature of molten salt. Complete burnup of nuclear fuel enabled by a combination of homogeneous liquid fuel, online chemistry, and thermal breeding, such as Alvin Weinberg and the team at Cornell intended to build until the molten salt breeder program was suddenly terminated.
Charles says, stop that MSRE reactor experiment, fire everybody, just tell them to clear out their desk and go home, and send me the money for fast breeders.
This is the thorium reactor.
Can you tell me what the thinking is on thorium as a fuel, what the advantages are, what the disadvantages are, what the pros and cons are of thorium?
The first commercial reactor operated in this country at Shippingport was based on thorium fuel.
My constituents were always asking me about this. Does thorium have a place in our nuclear future?
Can you make them work? Yes, you can make them work. Is there an advantage to doing it? I haven't seen it.
There's about 4 times more thorium on Earth than there is uranium. But at the moment, uranium is cheap enough that that simply doesn't matter.
It's, I think, one of these sort of technological cults.
An atom of thorium and an atom of uranium both contain the same amazing millionfold improvement in energy density over coal. It isn't that an atom of thorium contains any more energy than an atom of uranium, or that natural thorium is much more common than natural uranium. But we don't consume natural uranium in today's reactors.
There's about 4 times more thorium on Earth than there is uranium.
Thorium is 400 times as common as uranium-235. And we can't harness the full power of natural uranium with the thorium breeder. That's a bigger challenge. Just like today's reactors, any one piece of fuel will eventually become too used up to sustain fission before its energy potential has been fully realized. It is the semi-fission fuel which then must be reprocessed into new fuel or treated as waste. The elimination of fuel fabrication and the elimination of fuel reprocessing as a distinct step are essential if you want to harvest the smallest amount of natural resources and produce the smallest amount of nuclear waste. Because the economics of nuclear power don't favor reprocessing fuel, it will always be cheaper to simply dig up more uranium rather than using every atom you've already mined. The most environmentally friendly way to operate the thorium breeder is the only way to operate the thorium breeder. If you stop the chemical kidney, then fission slowly grinds to a halt. The chemical kidney lets us continually remove used fuel and keep adding fresh fuel. It is how our thorium fuel can be completely converted into energy and fission products.
People recycle cans, they recycle papers. Why not candles? I say we put a bin out, let people bring back their old drippings at their convenience.
It's like those bags that say, I used to be a plastic bottle. We could have a bin that said, I used to be another candle.
And then when they bring in those candles, we'll put them in another bin that says, I used to be another candle.
Yeah, and then eventually we could just have one that said, trust me, I've been other candles.
By weight, a paraffin candlestick and gasoline contain about the same amount of energy. Why don't cars run on paraffin wax? Because the inside of your car might need to look like this or like this.
What process do we run chemically based on solids? We don't. Everything we do, we use as liquids or gases because we can mix them completely. You can take a liquid, you can fully mix it. You can take a gas, you can fully mix it. You can't take a solid and fully mix it unless you turn it into a liquid or a gas.
You know, the people who build light water reactors, they're physicists and engineers, and this is a whole lot of chemistry that they're not maybe so comfortable with. So it's the chemistry of it that makes it so special, but it's also the bit that existing nukes kind of go, oh, you know, we're going into realms that I don't perhaps feel so comfortable.
In the nuclear space, there are other innovators. You know, we don't know their work as well as we know this one, but the modular people, that's a different approach. There's a liquid type reactor, which seems a little hard, but maybe they say that about us. And so there are different ones.
Although Bill Gates' traveling wave reactor is still advertised to the public as a mechanical device shuffling natural uranium fuel rods around, TerraPower sought and received a research grant from the Department of Energy in 2015. It is for the study of a uranium-fueled, fast-spectrum, molten salt reactor.
Can you make them work? Yes, you can make them work. Is there an advantage to doing it? I haven't seen it.
Unless you are using slowed-down thermal spectrum neutrons, thorium breeding offers no advantage over uranium breeding. Dr. Lyons' report's investigation of molten salt only includes fast spectrum, not thermal spectrum. That is why he sees no thorium advantage over uranium. Alvin Weinberg knew the kidney would be required. His team knew it before they even started constructing the molten salt reactor experiment. So it's a bit disappointing to see Weinberg's chemical kidney dismissed as a drawback that could be potentially eliminated. The last operational molten salt reactor shut down in the United States in 1969. It ran in a remote location. Research documents were kept in a walk-in closet. For 3 decades, we didn't even know this was an option. Then in 2002, Ornell's molten salt documentation is scanned into PDF and made accessible to some NASA employees. 2004, Kirk Sorensen delivers CD-ROMs full of molten salt research to policymakers, national labs, and universities. Dr. Per Peterson at Berkeley receives a copy. 2006, Kirk moves the scanned research onto his website. 2008, molten salt reactor lectures begin at Googleplex and are hosted on Google's YouTube channel. 2009, the very first thorium conference is held. Wired magazine runs a feature story on thorium. 2010, American Scientist runs a feature on thorium. International thorium conferences begin. Server logs show Chinese students downloading molten salt reactor PDFs from Kirk's website. 2011, China announces their intention to build a thorium molten salt reactor. In the US, Flybe Energy is founded. Transatomic Power is founded. 2012, Baroness Bryony Worthington tours Ornell's historic molten salt reactor experiment, which has never been made open to the public. Kun Chen visits Berkeley, California, telling us that 300 Chinese are working full-time on molten salt reactors. 2013, Terrestrial Energy is founded. 2014, Thorcon is founded. Moltex is founded. Seaborg Technologies are founded. Copenhagen Atomics are founded. 2015, a flood of technical details and technology assessments are released by molten salt startups. India reveals their new facility for molten salt preparation and purification. China announces that now 700 engineers are working on their molten salt reactor program. Bill Gates' TerraPower receives a grant to investigate molten salt. 2016, just as this video is about to be released, Miriam Tonloto releases a feature-length documentary about molten salt reactors called Thorium, the Far Side of Nuclear Power. Dr. James Hansen tells Rolling Stone magazine that we should develop molten salt reactors powered by thorium. And Oak Ridge discovers actual film footage of the molten salt reactor itself. Produced in 1969, it was forgotten in storage for over 45 years. It offers up our first and only glimpse of an operating molten salt reactor. As a communications asset, this is utterly invaluable and will be fully incorporated into future videos. In 2017, I think just about anything could happen.
The molten salt reactor experiment was one of the most important, and I must say, brilliant achievements of the Oak Ridge National Laboratory. And I hope that after I'm gone, people will look at the dusty books that were written on molten salts and will say, hey, these guys had a pretty good idea. Let's go back to it.
Back in the 60s, Alvin Weinberg saw the molten salt reactor as a means of addressing energy pollution and the need for clean water. Desalination would turn the Middle East into farmland. Power centers would co-locate energy-intensive manufacturing and small modular reactors. Surplus power would be sold to nearby communities. He knew energy was the ultimate raw material. The more energy you have, the easier it is to recycle and use virgin materials more efficiently. Given enough power, we can pull carbon right out of the atmosphere or ocean. One day, on our path towards such a future, they'll be talking about putting a molten salt reactor in your home state. It will create manufacturing jobs and produce electricity for your home. It will charge your electric car at night.
Give me a martini straight up with 2 olives for the vitamins.
You'll do things with energy that we can't even imagine. And you'll be kept safe by a chemically stable choice of coolant and gravity-powered passive safety systems. I don't know when we'll get to that point. Everyone's design is different. Everyone's path to market different. I suspect more than one will succeed. Before they do, I want everyone to know what molten salt reactors are and why they are.